Hey there. Okay, so this is going to be one of the videos I'm going to do on um, questions that a lot of people missed. As you can see from the little graph here, quite a few people had troubles with this one, and that's pretty much what the worldwide is. It's one of those things that once you get it, you go, oh, this is actually way easier than I ever thought it was. But when you're learning it, it's kind of, it's tougher. Okay, so here you're given some information. This is for benzene for this one. The question actually has a different ones it will pop up with different sets of information here and different values. But really, when you do these questions, they're all pretty much the same thing. Okay, and so you just do them all the same sort of way. You just use different numbers. So the first thing that I always do whenever I do these is I essentially just trace a little line here, and that's a heating curve, and so, or a heating plot, or and so this right here is where it's solid and you're heating it up. This would be the phase change, that would be from solid to liquid, and then this right here would be heating the liquid, and that will be heating it till it's the boiling point. Excuse me. And then at the boiling point, you're going to have energy going into the phase change, and so the temperature doesn't go up. And so that right there is the phase change from liquid to gas. And then finally the gas will heat up into wherever it finishes heating up. Okay, and so it tells you a 45 gram sample of liquid benzene is initially 54.2 degrees Celsius. If the sample is heated at a constant pressure, that's important because the pressure would change the phase changes. But all these pressures should be 1 atmosphere. Essentially every question I'll ever give you in this earlier chapters will always be for 1 atmosphere. That's a more advanced thing if you have to change pressure. So that's just telling you, everything that you know so far is fine. You're good. Blank kilojoules of energy are needed to raise the temperature of the sample to 96.6 degrees Celsius. Okay, so if we look at this right here, we start below 54.2 is below the boiling point, but it is above the melting point. So what we're doing is we're starting somewhere around here. It's going to be a liquid, and you're going to have to heat it up first, then you'll boil it, and then at 96.6 is where you end. And so 96.6 is above the boiling point. That means you boil all the liquid off, and then you're going to heat that gas a little bit, like 16 degrees. Okay, and so what we have to do then is we have to do this in 3 steps. There's the first step, where you're going to raise the temperature of the liquid to the boiling point. There's the second step here, which is going to be going from liquid to gas. And then there's the third step, which is heating the gas. And that's this little red section is what we're doing. You do this in 3 steps. 1, 2, 3. These steps, you could have the formulas and use the formulas if you wanted. Honestly, though, I personally find it much, much easier to just use the constants. So the specific heat of the liquid is going to be this right here, this section. And notice these units here. You can just do dimensional analysis, cancel off the units you don't want. All you want is joules here, because you want kilojoules eventually. And so all you need to do is cancel off the grams and degrees Celsius. The grams is going to be the weight here, and the degrees Celsius is going to be, of course, the change in temperature. It'll be going from your initial temperature here up to your boiling point here. Remember that anytime you do a change of, it's going to be final minus initial. And so you'll do 80.1 minus 54.2. That will give you your change in temperature. And I'll show you that again in type down here. Okay, and then this section right here, well, that's a phase change, which is a delta H. Specifically, it's for vaporizing something. You're going liquid, vapor. which is this value right here. Right there. I can't highlight it. Anyways, you get the idea. It's that one right there. That's joules per gram. So obviously you're going to just have to take and multiply that number by the number of grams. And that would give you joules. And that would be your second section. Your third section then is going to be, well, a gas. So you're going to have to use the specific heat of the gas. Remember, specific heat is for increasing the temperature of something. The delta H's are for phase changes. Okay, so let's go ahead and do it so you don't have to try to keep this all in your head. This is the formula, by the way, if you want to use it. That there's the specific heat, that's the mass, that's the change in temperature. Frankly speaking, I never bothered memorizing that when I went through school because you can just do dimensional analysis. Notice here's the specific heat for the liquid, because we're talking about the liquid in this first step. We're heating the liquid. We're heating 45 grams of it. And so we multiply this specific heat, which has grams in the bottom, by 45 grams. Grams will cancel. Then we're going to multiply that value by the difference between the final temperature, which is, again, it's not the final temperature of the entire process. It's the final temperature of step 1. And step 1 ends at the boiling point, which is 80.1. And so you take 80.1 minus 54.2. Remember to do that step first or in parentheses because that's the order of operations. And then you're going to take that difference, which is 25.9, multiply it by the number you get here after taking 1.74 times 45. And that's going to give you joules. And again, how do I know it's in joules? Well, I look at my units, and all I'm left with is joules. And so I have essentially 2,028 joules. Okay, so the next step is going to be the vaporization step. And I'm going to use the heat of vaporization, delta H of vaporization, times my mass. Again, you can use the formula, or remember Q is heat. That right there is the heat energy down here. That's an energy, it's in joules. Alternatively, again, you can use the dimensional analysis, meaning you just cancel off what you don't want anymore. And so you have a constant here, which is your delta H vaporization, which is 393.3 joules per gram. You don't want grams, you just want joules because you want heat. And so you're going to multiply this number here by your number of grams. Why are these the same numbers of grams? Well, changing the phase does not change the amount of matter in there. If I have 45 grams of liquid, I'm going to have 45 grams of gas, I'm going to have 45 grams of solid. It doesn't matter. Because I didn't change the identity, I didn't add any moles, I have to have the same amount of matter. I have to have the same number of atoms. I have to have the same mass. And so 45 times that is 17,700 joules, which is 1.77 times 10 to the fourth. Okay, and so now I do the final step, which is going to be heating the gas. And so again, I take the specific heat, but this time for the gas, which is 1.04 joules per gram degrees Celsius. I multiply it by the mass again, which is 45 grams. I then am going to multiply that by the difference in temperatures. Again, my starting point for this region, for that step, is my boiling point, which is 80.1. And it goes up to this final temperature here, which is 96.6. So I take 96.6 minus 80.1 and multiply that value. All right. Once I multiply these values successfully, I'm going to get 772.2 joules. That's a very small number compared to the others. I go ahead and add those all up. So this one, plus this one, plus this one. And that would give me a total of, for all three regions, 2.050 times 10 to the fourth joules, essentially 20,000 joules. I want this in kilojoules for my answer for my problem. Well, there's 1,000 joules for every kilojoule, so I take and divide it by 1,000. That'll give me 20.50 kilojoules. 20.50 being the correct number of significant figures, due to the fact that all of these are in 4 sig figs. Right there. Alright. And that's it. That's how you do that. Honestly, all 3 of these are different derivations of that same problem. And there's not really a whole lot of difference in it. You just, again, the easiest way to always do these is to trace out your heating curve, which is, again, a raising in temperature with the heat, which is heating the substance. So you start off as solid, you heat it up, the solid will then melt to liquid, and that's this right here, phase change. You don't have your temperature going up because the energy is all being used in phase change. And then you're going to heat the liquid, meaning the temperature will go up as you put in more heat. And then finally you get up to here where you're going to have your boiling point. At your boiling point, you'll have your phase change from liquid to gas. That's what boiling means. And that's just going to correspond to this delta H of vaporization. By the way, the lengths here directly correspond to these numbers here, if you're ever curious why those look like they do. And then finally, the last region that's possible is the gas heating. And again, you can just trace along this to select the regions you need to calculate each region, add them together, and that's your value every time. If you need to select what is happening due to certain conditions, like this problem, all you need to do is, so you have a lead sample, it's initially this temperature. If that much heat is added to the sample at constant pressure, which of the following is true, all you need to do then is go ahead and again trace out your graph here. And this time we're going to go going backwards. And so we look, and 317 degrees Celsius is below our melting point, temperature melting right there. And so that is going to be, well, a solid at the beginning. You're going to add heat to it, and so it's then going to go up this. And so then we need to figure out, well, what would that amount of heat amount to? If you're kind of thinking about it, and you've done a few problems, you actually could probably guess this one. Because we're not that far from the melting point, and this is a fairly small number, we probably just barely exceeded the melting point. And so it's probably a liquid. But let's go ahead and calculate it. That's just a way of guessing if you want. Simple logic problem. Okay. And so we will start in region 1 here because we were a solid at the beginning due to the fact that we're below the melting point. And so we're going to start at 317.00 degrees Celsius. That's what it's initially at. We're going to go up to the melting point right here, which is 328 degrees Celsius. And we're going to see how much energy that is. And so we take our 23.1 grams, we multiply it by the specific heat of the solid, so right here, which is 0.13. And so 23.1 grams times 0.13 joules per gram degrees Celsius. That's going to be times, in parentheses, the final temperature, which will be our melting point, minus our initial temperature we started off at. If we do that math, we'll get 33.03 joules. Notice that number is quite a bit smaller than what's been put in right there. And so we're definitely past that region. The next thing is we need to see if we manage to go completely from solid to liquid. Did we melt it? And so the next thing we're going to do is we're going to see if we melted it. So to melt your solid, you're going to take look up here, you have delta H of fusion, fusion being melting something. And so that is going to be 23 joules per gram. We'll take that number, we'll multiply it by the number of grams, so 23 joules per gram times 23.1 grams. I know they're almost the same number, but that's just coincidence. And that gives us 351.3 joules. Notice that would give us a total energy used so far of, I'm sorry, I said that 300, I got dyslexic, I guess. Anyways, a 531.3 joules. You add these two together and that will tell you how much energy you've used so far. And so this will be 564.6 or 0.33. 564.33 joules have been used so far. That is still less than the amount that we've put in. So 576 joules. So what we're going to do next is we're going to have to go ahead and do the remaining amount. And so to do the remaining amount would be, there's actually two ways you can do this. There's the way that your book would normally show you to do this, and then there's the way that I typically would do this. Let's go ahead and talk about the way your book sort of shows you how to do this. And so the next step you can do is you would figure out how much energy would take you up to this 328 right here. Okay. Notice that 328 is actually your melting point. And so if we, well, okay, we're actually done. I didn't pay attention to what the problem said. Notice that we had energy left over. The fact that we still have energy left over means that we have to be above our melting point. If we did not have any energy left over, if we did not actually accomplish the entire solid to liquid phase transition in this second step and still have a little bit of energy left over, we would have stopped exactly at 328 degrees Celsius. However, we are above 328 degrees Celsius because we're somewhere up on this heating the liquid, which has to be above 328 because that's the melting point. So that's actually done. We don't have to do any other math. You could find out exactly where you are by simply taking your specific heat times your mass, and then take your temperatures here, and you'd have 328 here, and this would be X then. So your value here for your temperature where you'd stop would be X. And if you solve for X there, you would actually be able to get the amount exactly of the temperature you stopped at. But we don't need to do that, because like I said, 328 is actually our melting point, and so we know we're above that because we had energy left over. Ooh, I need water. Okay. Please let me know if you don't understand anything on this. Again, I'll just make videos for the ones people have a lot of trouble with.